Hello, everybody, and welcome to another week, another episode of Dome to Home. My name is Jeremy. As always, I will be the navigator for today, which means everything you see over here on the dome will be controlled by me. Now, this week we've got Rami. Rami, how you doing today?
I'm doing fantastic. How are you, Jeremy?
Oh, doing swell, doing swell.
Stellar.
Hey, good joke. There we go. Let's see how many good jokes we can get in this week. We're at one.
We're
Awesome.
at one. We are at one. I think we're doing fantastic.
We're on a roll.
Also helping us is our question master and chat moderator, Tara. If you have any questions, either send them directly in the chat or submit them through our Google form. There's a link in the description of the video, or it's also pinned in the chat. So last week, Tara talked about just how much water there is in our solar system on planets, moons, dwarf planets, comets, asteroids, etc., everywhere. But how did it get there? And where does water come from at all? A mystery. Actually, it's not going to be too mysterious by the end of this video, hopefully. So to figure that out, let's quickly unpack what water is. So water, also known as H2O, is a molecule. Molecules are like little structures made from atoms, which is the smallest unit of an element that you can get. There are a lot of elements, as you can see, and a lot of these can come together to make molecules. We can kind of think of these atoms of the elements as being like Legos, with each element having its own Lego. So what makes an element different from another is how many electrons are in the atom. So as you move up the table, there are more and more electrons. So in our Lego analogy, we're going to equate those to the little studs, the circles on the top. So the most basic element is hydrogen, with one electron, so one little Lego stud, and then so on and so on. So if we think of them like little bricks, if we think of a water molecule, we've got oxygen and hydrogen. Oxygen has 8 studs, 8 electrons. So we can think of it as having a brick with 8 studs and 2 bricks with 1 stud. We've got our nice little water molecule. But where did the Legos come from in the first place? Where's our Lego factory? Yeah, there it is. Yeah, where's our Lego factory? So to answer that, we are actually going to go very, very far back in time. So we're going to go all the way to the creation of the universe about 14 billion years ago. So you may have heard of the Big Bang Theory. It goes that all energy and matter in the whole universe was concentrated into a singularity, which then exploded, hence Big Bang, and inflated out and out and out and out, etc. And that's our universe now, 14 billion years later or so. So at first, the only elements were a very simple hydrogen and some helium, which would be like our 2-stud Lego, which cool. Now we have hydrogen and we have some helium, but there are a lot more elements out there, right? Including oxygen. We can't make water without oxygen. Hydrogen is not oxygen. Fun fact, hydrogen isn't oxygen. Hydrogen isn't water, it's fine. So we need to make more Legos. We need a factory. We need an element factory. So let's take a look. That's where stars come in. So as the universe cooled down a bit from that initial explosion, matter started to come together due to gravity. And eventually those clouds of hydrogen collapsed into stars. So stars, the core of a star is under just so much pressure. Ooh, yeah, we've got a really cool thing here. This is like gas and dust in the universe, and because of gravity, it's kind of coming together, and it's going to make the stars. So the stars are under a lot, I'm so sorry. I ran out of water, are under a lot of pressure. I ran out of water in a show about water.
Ironic.
Ironic, isn't it? So it's under a lot of pressure. So in the core of a star, there's so much that we can start actually making elements. So we've got our little hydrogen bricks, our little 1 studs, and we can actually, when you push 2 Legos together and now you have 2 Legos next to each other, we can actually make it so it's now 1 Lego, a whole new one, a whole new element. We have hydrogen turns into helium with our 2 studs, right? Like that. So, it fuses all of this hydrogen into helium, and then it runs out of hydrogen And they're just really, it's this inert helium core. And it kind of starts shrinking because of pressure from gravity. And then eventually it starts fusing helium into carbon. And that's where smaller stars like our sun, that's kind of where we stop. But in larger stars, the process just kind of keeps going and going. And you end up with kind of like a gobstopper star with all of these layers. You can see over here, all of these layers have like different types of fusion happening in them. So different elements are being made in little different sections of our element factory, our Lego factory, our star. And it just makes more and more and more and more. Yeah, you can see the gobstopper here. Yeah. And eventually it's going to hit iron. And that's when fusion stops and ooh, boom. There we go. We hit a supernova. So for smaller stars, it's a little less dramatic. They just kind of push the outer layers off. But we've got really cool supernovas with the big ones here. But either way, we end up with these beautiful clouds of gas and dust made out of all these cool new elements that we've made. And even molecules can form these clouds, or nebulae over there. So we've added a bunch of new elements to the mix. It's not just hydrogen anymore. It's all of these other ones. And we can collapse our cloud again to make a new star. So the universe is just fantastic at recycling. These nebulae collapse into stars, explode, collapse into new stars, explode, that sort of thing, for as long as the universe is going to keep going. So when they collapse into stars, they actually also collapse into protoplanetary disks. So it's not just the star at the center. There's actually a bunch of material circling the star, or the new star to be.
Oh,
so
sorry.
those are, well, no, go for it, Jeremy.
No, I was just going to ask you if you wanted to show something else besides these ALMA discs.
Yes, absolutely. So those are the ALMA discs. So ALMA is a telescope. It's a radio telescope, and they got actual pictures. This is like radio waves, but these are real, actual protoplanetary disks that we see. So you can see there that all of that stuff is circling a star. The ones that have rings, planets are being made, but we have a really cool clip to show you that it's a computer model that can kind of show you what it would look like.
Yeah, let's go ahead and switch to that now. So here you see that disk, kind of a simulation of those disks that the ALMA telescope has been able to take images of, and it's going to zoom in here a little bit. So this is like an early solar system, and then it'll zoom in to a little patch to get a close-up view of what's happening in this disk. So you see everything is swirling around in this big cloud around, dust and gas, and then gravity eventually starts to pull, on all this matter, and it starts to clump up, and you can see little kind of balls or little clumps of material will start forming into what we call planetesimals, which basically is just the interior of a planet, or little baby planets. We'll see it zoom out again. And then you can see where these little planetesimals are forming. You get these nice dark rings that you could see in these ALMA disks that I can show you guys again. And that is where these planets are forming and kind of, accreting all of this material as it moves around in our early solar system.
Yeah, so these disks are just filled with all manner of elements and molecules. The most common element is, you might have guessed, hydrogen by a long shot, then helium, then oxygen, which is really convenient for making an element like water that requires hydrogen and oxygen. So these elements, all of them, they come together to make, all different types of molecules, not just water, but also things like carbon dioxide or methane, or more complex molecules like hydrocarbons, things that we need for life. And now we can make those planets, asteroids, comets, etc., with more than just hydrogen. So because the molecules are all throughout the cloud, all throughout the disk, they're found all over the solar system once it's formed, right? That's why we have water all over. But the state your water is in depends on the distance from the star. So the closer you are to the star, it's hotter. And then the further you are from the star, the colder it is, right? So you are really far from the star, you're going to end up with like water ice. If you're too close to the star, it's going to evaporate into vapor. When you're just the right distance, this nice little Goldilocks zone, as we call it, or the habitable zone, you get liquid water.
Yeah, and a
That's
good thing to point out here is that these distances are measured for liquid water on the surface. I don't know if you already said that, Remy, but you might think, well, last week, for instance, we talked about there being, icy moons and like maybe subsurface oceans of water. When we talk about the Goldilocks zone with exoplanets, or whether it's in, with planets in our own system, it's the distance requirements for liquid water on the surface of these bodies.
Yeah, there's a lot of things that can kind of change where liquid water might be. For example, an atmosphere can make it kind of warmer, so your habitable zone could be a little bit further away. If your star is really hot, then your habitable zone is much further away. If it's a cool one, it's closer. If you have another source of heat, then you can have liquid water, but still be, further away. So this is just kind of the basic idea of where from, like, the distance from the sun, just on the surface. So sorry. So hotter, not as wet. You're evaporating further out, cold ice. And we find water in all of its forms, just like everywhere in the solar system. But you've noticed maybe that there are some places with more water than others. Like Earth has a lot of water, but places like Venus or Mars don't really have a lot of water. So keeping the water, it's a matter of distance. Yeah. Also protection from the sun, size. Earth is far enough away that the water isn't evaporated. It has a magnetic field to protect it from the sun. And it's large enough that it has the gravity to hold on to any water vapor. So if you want to learn more about how Earth kept its water versus planets like Venus and Mars, definitely come back on the 24th. We're going to have a special presentation from Dr. Dave Brain on the subject, and that should be fantastic. But the original water from Earth's formation did start out like the ocean that you can see, in this picture. It was likely evaporated water vapor. It was a gas due to the extreme heat at the time from the formation of the planet. So it was all water vapor, and it became clouds, and then eventually rained water all over the planet as it cooled down, which was probably a heck of a rainstorm. I would love to see that. But actually not all the water here on Earth was actually here from the beginning. So, you've got the water from creation, but a lot of water actually came from comets and asteroids crashing into the planet.
And we've got some pictures of comets and asteroids that I'll show once the system wants to catch up. Froze on me a little bit. That's okay.
Live show.
Here we go. Nice. Some collages of some comets there in the center and the top and the top left, and then some asteroids and other objects kind of all on the right-ish side of the screen there.
So comets especially have a lot of ice in them, and we can actually see this. We can see when they get close to the sun, we can see them sublimating. So that's when ice turns to gas instead of just evaporating as they get close to the sun. So yeah, there's a really cool picture there. You can see where, like, away from the sun, you have the ice from the comet coming off as a tail. That's why they're just so pretty. So comets carry that water with them. And if they hit a planet, the planet gets a nice delivery of water. And if enough comets hit over millions of years, the millions of years Earth has had to get comets hitting it, you end up with a huge delivery of water. So you can see there, as it comes closer, you can see that the ice kind of comes off, and they get really far away. That's kind of what makes a comet. So early in the solar system's formation, there were a lot more stray comets and stray asteroids and such running into the planets. So a lot of water actually came to Earth from those frequent impacts. So exactly how much water came from each mechanism is kind of up for debate. How much of it was here intrinsically already from formation? How much of it came from comets or asteroids? It's an active field of research. But water is integral to life as we know it. And we're still not 100% sure where it all came from on our planet, which is wild. But as we learn more every day, we can fill in the blanks between the creation of the universe and the water that we use every day. Ooh, those are comets.
Yeah, so I brought up these are all the orbits of the short period comets. So the ones that orbit more often than the long period. And I'll kind of orient us out here a little bit, and maybe we'll bring up the Earth's orbit here for some reference here. So you can see these comets are actually pretty close in comparison to where the Earth orbits. And then as we zoom out a little bit further, we'll bring up some long period comets. These are ones that as they take much, much longer, these blue lines take much, much longer to complete their orbits as they go to the outer reaches of our solar system, kind of refreeze into big balls of, or slushy kind of snowball, dirty snowballs, and then, come back in and swing around that sun and heat up and sublimate all that ice.
Yeah. So all this stuff is carrying a bunch of water. And actually, Jeremy, you have a favorite comet, right?
Yeah, I do have a favorite comet. I like talking about this. I love bringing this comet up in shows because it is actually a comet that came to the Earth and kind of came by this year. And so a lot of people might be familiar with it. And if you're not, here is that comet. It's not the comet that you were thinking of, which is Neowise, but this is my favorite comet because we actually got my comet, this puppy comet, the week after Neowise came by the Earth. So it was my favorite comet, and he's a cute little puppy, and there's a little pumpkin with a comet on it in my best pumpkin carving skills. So there's 2 bad space jokes, I think. Maybe 3. We might have slipped 3 in there.
That's the goal.
But yeah, comets are really great.
Yeah.
Both K9 and snowball forms.
Yeah.
I love them.
Gotta love comets. We have plenty of time for questions. So if anybody has any questions about how water came to Earth, what water is, anything that we talked about Jeremy's dog, space in general, feel free to either drop them in the chat or submit them in the spreadsheet, and Tara will let us know.
Yeah, what do we want to know about comets? Drop those comet questions, or not even comments, just
maybe water questions.
Water questions, I guess.
About water.
Now my mind's on comets, but it can be comets, it can be anything that has to do with water. Early solar system formation, asteroids, whatever you can think of, whatever you want.
We do have a comet question.
What is
so
a
how
comet
are comets
question?
and asteroids different?
Ooh.
So, yeah, if you could, Jeremy, can you pull up the orbits again for comets and asteroids?
Mm-hmm.
So the biggest difference that you're going to see between comets and asteroids is their orbit. So asteroids, you're going to see them a lot closer to the sun. A lot of times they're actually pretty circular too. And we actually have a whole asteroid belt even. That's a bunch of asteroids all circling around between the orbits of Mars and Jupiter. Comets, on the other hand, have these huge, wild, wacky orbits that are just super far away, come in close. We call those elliptical orbits. So they're not very circular. And those are what comets are. So there's your biggest difference. Because of that, the difference is also in composition. So your asteroids are going to be a lot rockier, whereas your comets are going to be icier. Who knew? So
Who knew? There we go. So we see these are the main belt asteroids. You can see that they're also all orbiting, as Rami said, in kind of more or less the plane of our solar system, as a nice kind of cohesive belt around in between Mars and Jupiter. And some of these comets most of these comets are not following much of any pattern. When we look at this, they're very inclined to our own plane of our solar system. They go very far out. They go kind of very far in. Yes, and they get much closer into the sun than all the asteroids. All the asteroids kind of are roughly at the same distance, from the sun as they complete an orbit, where comets come in very close and then they go very, very far out on these very highly elliptical orbits, as Rami said. That is a great question.
Yeah, thank you for that question. It's a good one.
Let's see, what other questions do we have about water and where did it come from?
Here's a good one. So how does water get from inside a planet to the outside? So talking about the formation, we had all of these elements and they're all coming together to make planets. We didn't really talk about how certain elements get to a different part of the planet. So you end up with like different elements because some elements are heavier and they kind of almost sink to the bottom of the planet. And then lighter ones kind of end up at the top. It's called differentiation. Water, though, ends up coming out through things like volcanoes and faults and stuff. It releases the gas that was inside the rocks by being hot. And that's how we actually ended up with our early atmosphere, was from volcanoes erupting and blowing off steam with water and with carbon dioxide, etc.
Seeing if I could find some pictures of some volcanoes.
Ooh, I love a good volcano.
I know. You'd think I could find one. We'll see. We'll see if some other questions.
Land and water. So versatile.
Volcanoes. Here's a picture of some lava. That's not quite the picture of a volcano I was thinking of. There's some different types of volcanoes. There we go. That's not that bad. So you could see it, actually, especially on this is actually not bad. You could see how those magma chambers go really, really low, or deep into the kind of the interior of the Earth. And so it works to transport that inner material up to the surface.
I've got another question. If water forms in space, is it water or ice? So when we say water, usually what we're referring to is just the H2O, the molecule with the 2 hydrogen and the oxygen. So that's why usually you'll hear astronomers and scientists talk about liquid water or water ice, water vapor, because it's all water. It's just a matter of the state. So it is water, and ice is water, as long as it's water ice. But usually when you've got things in like these molecules in these big clouds of gas and dust, I would say it's almost more like a vapor because the molecules aren't very close to each other at that point. What would you say?
Yeah, I think you kind of covered it a lot. Let's see. The question was if water forms in space, is it liquid or ice? Is that what the question was, right?
Yeah, is it water or ice if it forms in space?
I would think that you couldn't just have a piece of ice floating around. Well, you would need a lot of molecules together. Yeah. In like nebulas, you would have, gaseous water vapors.
Nebulas look like they're like really thick, but a lot of times they're actually pretty sparse. There's a lot of space in between things.
Mm-hmm.
So the water molecules don't tend to be particularly close to one another at the start. Ice being a solid, there needs to be a lot of them in a specific structure.
Mm-hmm. Yeah, so you wouldn't have any like chunks of ice forming out in like a nebula.
Mm-hmm. Be cool though.
Yeah. You need big objects like planets or like moons or something to be able to like form all that ice like on the surface.
Yeah, that's why it takes so long to make a planet or a moon. It's all going to come together. So we've got, does it rain or snow on other planets? And the answer is yes, there is weather on other planets. As long as you have an atmosphere and you have something to make a liquid, then you're going to have some sort of weather. So it does actually snow at the poles on Mars, for example. But yeah, as long as you have some form of liquid and you have an atmosphere to like make different temperatures in places, you're going to get like rain or snow.
Mm-hmm. Yeah, and I think it's mainly carbon dioxide ice that snows, or carbon dioxide snow, right? It's mainly not water ice.
I should specify. It doesn't necessarily have to be water every time. Yeah. On Mars, it's mostly carbon dioxide.
But places like this here, we have Pluto and Charon here. Pluto in the lower right here, and Pluto, being one of the dwarf planets in the outer solar system, it has these massive nitrogen glaciers and also full mountains of water ice, which I think is very, very interesting. We didn't really think that there would be that much water maybe out there on an object like Pluto, but, especially when New Horizons went by, kind of changed our ideas of where water was in the solar system. And then, as we talked about last week a little bit, just the study of the Kuiper Belt and some of the objects there, finding different amounts of water in the Kuiper Belt has really made us think that water is located in very, it's a lot more abundant than you might think.
Mm-hmm. It's everywhere. We actually talked a little bit last month in our exoplanet series about water being on planets like outside the solar system too. So there could definitely be planets like ours with the same type of weather, like rain and snow. I hope there's a lot of snow in the solar system. Yeah. I love snow. Honestly,
I think, correct me if I'm wrong, Rami, but I'm pretty sure, hydrogen's number one in terms of a universal abundance, the elements. And I think oxygen is number 3.
Yeah, so
it's hydrogen, helium, oxygen.
Oxygen, yeah.
So there's lots of hydrogen and oxygen out there. It's just really a matter of, if we're in the solar system, how much was there when the solar system was formed, and how much actually gets transported to it. And we are learning more about it every day.
We've got plenty of Legos. We just need to build the things.
That's right. Never stop using those Legos.
I like the Lego analogy. I loved Legos. What can I say? Well, if there are any other questions, now's the time to drop them in the chat or in the survey thing. That's the link.
Final questions.
Right now for some reason. The only word I can think of is spreadsheet.
Spreadsheet? It's kind of a spreadsheet.
It's a form. It's a form. It's a form. Fill out the form with a question. But otherwise, I think we can go ahead and call it. I hope you learned a little bit more about water in the solar system, water on Earth, where water comes from at all, how we get so many Legos here in the universe, and dog comets. What can I say? If you think of anything after the fact, feel free to submit it into our question form, and we'll get that and address it in the next show, or leave a comment here on the video. Don't forget to like the video if you enjoyed it. Subscribe to our channel if you enjoyed it. Turn on the little bell for notifications for videos like these, and absolutely share it with a friend who might enjoy it.
That's right. All right, everybody. Until next time. Thank you so much.
Thank you.